Welcome back, AP Statistics. We are in part 3 of chapter 7. We are going to be finding a regression line using just raw data, raw bivariate data, like these bivariate data right here, relating the birth rate, which is calculated by number of births per 1,000 people in the population. And the Y variable is female life expectancy in years. All right, so first what we're going to do is graph a scatter plot and confirm the criteria for computing the regression line. That is that we have quantitative data. Well, that's a check. We don't even have to graph anything to confirm that. A linear pattern, we will need to look out for that, and no clear outliers. So let's go to the calculator and see if we can do just that. So here we are at the calculator. I'm going to go into Stat, Edit, and I've already entered my data to save time. If I want to graph this scatter plot, I'm going to go to Second, Stat Plot, make sure the plot is on, and make sure it is set to Scatter Plot. And as always, we go to Zoom, and we go to Zoom Stat. Okay, go to Zoom Stat number 9. All right, that's looking pretty linear, and there are no outliers. It appears as X increases, Y decreases. There is a linear pattern. Now we're going to move on to the second step. We're going to compute the regression line using linreg, well, whatever you'd like. There are two options. I prefer to use linreg t-test. It's a good one-stop shop for all things linear regression. And then we're going to write the regression line in the form predicted life expectancy equals blah, 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 birth rate. Let's have at it. So from here, we're going to go to Stat. We're going to go to Tests. And near the bottom is linreg t-test. The X list is list 1, the Y list is list 2. Don't worry about any of this other stuff. Scroll down to calculate and hit calculate. And there we have it in the form predicted Y values. The calculator does not put a hat there, though there should be. A plus BX. That's exactly the form we're looking for. So we need to find what A and B are, right? So this, in our book's context, is B sub 0 and B sub 1. So A, or B sub 0, is going to be 81 point all that, which will round to 0.6915. And for B, which is our B1, would be negative 0.4708. So those are our values. We can input that into our regression model. So we can input our values. There's our B sub 0 and our B sub 1. And we can state their units as well. The units of B sub 0 are the same as the units of the Y value, which would be years. And the units of B sub 1 would be the units of the Y variable over the units of the X variable, which would be that. The years per number of births per 1,000 in the population. Before we move on, I think some of you, just have a hunch here, some of you might want to see this regression line in action, superimposed on your scatter plot. Here's how you do that. You're going to go to Y equals, right? Y equals, your good old friend from algebra and pre-calc and all those fun classes. You're going to go to vars. Interesting place to go. But if you go down to statistics, number 5, you'll see a familiar friend under the EQ, which is short for equation. And here are some variables. But we want the whole regression equation. So we're just going to stop here at number 1. Hit enter. And it spits out the regression equation. Now I'm going to go to graph, and look at that. It's beautiful. So you may remember from the last video that I mentioned there were 3 conditions that had to be met for us to do linear regression and that there was an additional one. There was a fourth condition that had to be met, but we couldn't learn about that one until we had more context, all right? So this is the context that's going to help us understand the fourth condition. So recall that a residual is an observed value minus an expected value. Or we would say E for residual, just kidding, E is for error, and error is another name for a residual, is equal to Y minus Y hat, an actual Y value for a data point minus the Y value that the regression line predicts. All right? Data values are not usually going to be on the regression line. There's some distance between, or rather displacement between a point in the data and the regression line, and that residual is what we are concerned with right now. So the linear model relating hurricanes' wind speeds to their central pressures was max wind speed is equal to such and such and central pressure. All right, so let's use the model to make predictions and see how these predictions do. Question: Hurricane Katrina had a central pressure measured at 920 millibars. I guess that's a unit of pressure. What does our regression model predict for her maximum wind speed? How good is that prediction, given that Katrina's actual wind speed was measured at 150 knots? Knots? A knot is a nautical mile per hour, which a nautical mile is different than a land mile. Only the British could get away with that. So, how good is the prediction, given that Katrina clocked in at 150 knots? Well, here is the prediction. We would put 920 millibars into central pressure to find the max wind speed. After substitution, we have a predicted max wind speed of about 134.5 knots, nautical miles per hour. So the error would be the actual data value, which is 150, that's definitely a rounded number, minus 134.424, which is going to be 15.576. The actual data value was bigger than the predicted data value, which means that the prediction was 15.576 knots too low. So we're back to sunny Saratoga, New York. Our linear model for Saratoga homes uses the size in thousands of square feet to estimate the price in thousands of dollars. We are familiar with this equation at this point. Suppose you're thinking of buying a home there. You've heard so much about Saratoga, New York. You feel like it must be a place where statisticians are destined to go, so you might as well look for a home there. Would you prefer to find a home with a negative or positive residual? All right. Would you prefer a negative residual or a positive residual? Think about that equation for residual. Pause the video and unpause when you want to check your answer. All right, I'll assume we're ready to continue. I would want a negative residual. That would mean that the house is less expensive than we'd expect. If I had a negative residual, if you recall, the formula for residual or error is actual data value minus predicted data value. If E is negative, then the actual data value is less than what we predict, which is ideal. So 12 really sets up things for 13. You plan to look for a home of about 3,000 square feet. How much should you expect to have to pay? Well, it's so much as substitution for this one. You have the size of your house in square feet. Substitute it into the model. The model predicts a price of $8,400, that's this $8,400, plus 88.67 times the size of the house in square feet is 3,000. Plug and chug, you have $274,410. So now we're set up for 13. You find a nice home that's selling for $300,000. What's the residual? Remember, residual is the actual data value minus the expected data value. So we take our actual data value, 300,000, subtract our expected data value, and we find that this house better be real nice because it is $25,590 more expensive than our regression line has predicted. Our next step is to learn what a residuals plot looks like. Now, here's a really simple plot, just for the sake of clarity. We have a regression line going through 4 data points. We're going to plot the residuals atop our data. For the first point, the residual would be positive 1. We predict that at an x value of 0, our y value is also 0, but it's actually 1. So our residual would be 1. For this point, we predict that the y value is 1, but our point's down here at a y value of 0. So the residual would be negative 1. For this point, it's actually at a y value of 3, but we're predicting it's at about 2.5. So the residual would be positive 1/2. And for this point, it's the same as this point right here, except it's 1/2 below the predicted y value. So the residual would plot at about -0.5. So the reason we want to learn about a residuals plot is because we want that residuals plot to be boring. Though we are interested in finding patterns in the data itself, specifically a linear pattern, we don't want to find a pattern in the residuals. The residuals of the roller coaster data are graphed to the right, and it's a delightfully boring residual plot. I can't find much of a pattern in these residuals, and that is a good thing. Why is that? The absence of a pattern indicates that data fall evenly on both sides of the regression line in a chaotic way, meaning that a line is appropriate for the data. Okay, so the line we fit to the roller coaster data is reasonable. The residuals seem split half above and half below, and there's no pattern to them. A graph of residuals that bends or has pronounced outliers means that perhaps a linear model is not appropriate for the data. To demonstrate what I mean by that, I'm going to have my assistant Drake come on the scene. Well, Drake says no way to these bad residuals plots over here. We have this bending curved pattern right here. No way, says Drake. We have this outwardly opening fan pattern, complete with a couple of outliers, maybe. And Drake says, no way. But we like these residuals. There's no pattern whatsoever, and that means a linear model is appropriate. So now we have the complete story on the conditions for analyzing data with linear regression. First, all variables are quantitative as opposed to categorical. The data suggest a linear relationship. There are no outliers. With large data sets, you can get away with 1 or 2, but ideally no outliers, and there is no pattern in the residuals. None of this fan pattern or curved pattern stuff that Drake doesn't like. So we've come full circle, and we're going to be analyzing the residuals of the same bivariate data that we started the lesson with. So once you've computed the linear model, that's important. What we're about to do will not work unless you have used linreg t-test or some other linreg feature in the calculator to compute the linear model. You need to do that first. So after running linreg t-test, you can plot a scatter plot of the residuals by plotting L1 on the x-axis and second list residuals on the y-axis. I'll show you how to do that in the calculator. So we're going to do this for birth rate versus female life expectancy. And remember, we are looking for a non-pattern. We are looking for chaos. That's going to confirm that a linear model is appropriate. So one more time to the calculator. We're going to go to second stat plot. We're going to turn this plot on. And we are going to go down to our X list. We want that to be list 1. But our Y list, we're going to go to second. And list is above stat. So we're going to do second list. We're going to go all the way down to number 7, which is residual. If you have not computed the regression line, you will not have that option available. It's only available once you've computed the regression line. So we pop the residuals in there, then we can go to zoom, and we'll go to zoom number 9, zoom stat. And look at that chaos. Looks like a linear model is appropriate for our data.